Hello, everyone, and welcome to our 2023 March Edmonton R user group meetup, where we're going to talk about the simplest linear model function in R called LM and some of its competitors. Also, we are going to be looking at not just LM, but some other functions as well, which do very similar things, but maybe in a more automated way. But first, we are going to spend some time with understanding how we can use LM in a labor-intensive way, and then we are going to make some headways into easier, more automated setups. And since this code has been sitting on my computer for quite some time, probably I wrote it at a point in time when tidy models weren't available. And so that's why it is going to be relying on base R and base plotting methods. So that is just a caveat there. If you're looking for ggplot objects or tidy model and non-standard evaluation, this might not be the place to find that. But hopefully we can still learn something new and exciting about one of these little functions that are just there in base R. You don't need to load any package. So I have an R markdown, which I'm going to upload to the YAGROG website as well as a neat PDF or just the R code itself. So you'll be able to go there and grab it and reproduce it for yourself. If you want to install the dependencies, I'm going to announce this is a package I wrote a while back, and it just got published on CRAN as its first release because, well, there are a couple of packages that can do the same thing, like pack, remotes, renv, and why do I want another package for the same thing to just figure out all the dependencies and install? Well, sometimes I just need one line and I want everything to be ready. And other frameworks are more concerned about reproducibility and pinning the exact versions. This is just a really crude way of, please scan all my R scripts, figure out what packages are used, and install all of those. I don't care the versions. I'll try them, and if it's not working, then I'll add the note, and you can use the comments about the versions or repositories and everything. So it's like Roxygen style comments, and then dApps will be able to pin those versions if you have to. Otherwise, it is just going to grab the latest version from CRAN. I already have things pre-installed, but probably for you, if you're running this will be the easiest way to get everything set up. Now, set.seed is a handy little function that sets the seed, as the name implies. And what that means is as long as your R version is similar to mine, at least 4.0 or later, you're going to get exactly the same results. The random number stuff has changed before and after 4.0. That's why if you're really lagging behind in terms of R version, this might not be the case. So set C2, that just means the pseudo-random number generator is going to start at the same place, and we are going to get the similar results as long as the code stays the same. So what I do here, I set the seed, and then sigma squared, I set it to 1. We'll come back to this number later. N is 100. This is how many observations we are going to simulate under our data generating model. You can see it here. These are all now set. So now we are going to generate some variables like x, which means as x is changing, we're going to have a dependent variable along the y-axis. And depending on the value of x, y is going to be a function of x. So to make things simple, I'm just picking random uniform numbers between -1 and +2 and sort them. So this is what this line 30 is doing. X becomes a sorted random uniform 100 number in the range of -1 and 2. We can verify that this is really uniform. Well, 100 is not a huge number, but that's why you see some raggedness here. Now we take X and calculate a nonlinear function of X. We use some sine and cosine functions to make this look not so angled and linear. So we can plot mu as a function of X. This is how this looks. So we're going to try to fit a model which describes this shape. Now, this is not our real data. This is the true relationship between our unknown variable and some value of X. And X can be temperature or date, something that kind of looks cyclical, or maybe not. Maybe this is just how this function looks, and there is nothing like in terms of returning to the same value again and again. We don't know. This is just the data I made up, and I was trying to make it hard for LM to work out of the box. Now, epsilon, this is where our sigma square comes in. And if you look up the help page for R norm, which is random normal numbers, if you want to get 100 random normal numbers with 0 mean and some variance, then this function expects the standard deviation, which is the square root of the variance. So the sigma square is going to be our variance. So this is the variance of the error around each point. So as you look here, we have mu, which is our mean. So if you center the normal distribution around this point, now this becomes your mean, which is 0 in this case because we are going to add up the two numbers. So our mu, which is this dot, plus some variation around that. So we're going to draw another random number now, which is going to be our y. So y becomes, oh, I need epsilon first, and the hist of EPS looks like this, normal-ish looking, but due to small sample size, it's not as nice and pronounced. So we're going to add them up. Y equals mu plus epsilon. And now we can plot. So you see, this becomes quite noisy. Let's add in the line that we had before. So this is our true relationship plus some error, which can be due to many things. Right now, we are just setting it to a certain number, which is relatively big compared to the variation, the range of these mu values. But that's okay. We're still going to be trying to approximate this shape. So this is the data that we are going to work with. And with our fit, we'll try to approximate this gray line from the data 100 dots that we have here. All right.
So this is not a parametric distribution. We're going to do linear regression anyway.
It is parametric because, well, in the sense that we have some parameters that we are going to use, but we are not generating under some known beta values. So we could do something like this, like x times beta 1 plus x2 times beta 2 plus beta naught, which would be our intercept, right? We could do something like this, but I was just using this sine cosine function, which is, these are not the parameters that we are going to get. So in that sense, we are not simulating the data under a known linear model, but we are generating it from a smooth function. And the parameter here is that we know the mean values. So each mu could be a parameter, and we know the variance of the error around those. So the way how we generate this data, which implies something that maybe in nature, this is how the data is created, and we observe y, but we don't really have any idea about what mu could be, right? So what you observe is x and y, and you're trying to figure out what mu is. So in that sense, it is a parametric model, because we are going to estimate parameters, right? And then later we are going to cover some non-parametric approaches where we're really not trying to estimate parameters and try to attach meaning to those parameters, but we're going to be focused on prediction only. So how we can best figure out what this line is, irrespective of whether coefficients make anything or not. So in this sense, we're going to fit first a parametric model, but those parameters would be as meaningful as you can imagine, that like 0.1 means that there's an effect, right? So we don't really know much about the system other than x is between -1 and 2. Is this answering your question?
I'm deferring to your knowledge, and I'm going to follow along and learn.
All right. So this is what the data looks like. Now we can put together a data frame with different orders of x. So the structure of our data frame would be like this. X is this number between -1 and 2. X2 becomes x squared, then x cubed, then x to the 4th, 5th, and 6th. And these are way of fitting this linear model with polynomials, but these are not orthogonal to each other. These are just simple x to the power of something. And as we put this together, this is one way of, modeling this relationship, is that we fit models with increasing complexity. Here, I'm just highlighting 4. M naught is going to be just, we're using now LM, which is that famous linear model function from R. And the formula interface has its left-hand side and right-hand side. So that means we have a variable y with 100 observations that is our response. This is a function of something else on the right-hand side. So this tilde separates the right and the left-hand side. D just stands for look up these y and x variables in that data. For example, a data frame that we just created called D. +1 means we're not using any of the columns, we are just using the intercept, which is going to be the mean of y. So let's fit this. And summary M naught, you see it says intercept 1.2406. If I calculate mean of y, I get the same number. So this is the intercept. Now, if we keep adding x, then x2 and x3, we're going to get summaries with all those coefficients. Now, besides the intercept, which is not the mean anymore, because now it gets added as intercept plus 1.8 times x plus 2.06 times x2 minus 1.2 times x3, and so on. So this is now compared to our previous summary, where it didn't even bother to give an R squared, which is our goodness of one of the goodness of fit metrics that you can get. Now it's 0.58. That is quite decent. And other methods for this M3 object, which is a linear model object with this call that we just used, formula equals y tilde whatever columns and data frame D, and it gives us the coefficient. You can also get the coefficients this way, coef. This is a method quite widespread in other packages as well, to pull out these parameters. These are the parameters of the model. So if now you calculate like this, that the fit is the first coefficient plus the second coefficient times the first, like the x column, and then the third coefficient times x squared, and the fourth coefficient times x cubed, then this is going to be our fitted value or expected value. And there is also a method for that. Fitted M3 is supposed to give the same result. And you can see it lines up nicely. If we add an AB line, 1-to-1, then they are going to be exactly the same. So this is what fitted is using. So you take the coefficients and multiply it with something of a matrix like this. So if you take the right-hand side of the formula, then you get these columns pulled out from the data frame D. So now if you multiply each row with the coefficients, 1 times intercept, x times this x coefficient, and so on, you're going to get exactly these numbers. Does this make sense? Any questions so far?
So I just have one thing. So it may be like, so you don't have the y variable in the data. That doesn't matter. You don't have the data frame.
Yes.
You don't have the y
I
variable.
could have it there, and you're right. I don't have it there. So if I put it in here, then I think things will work out the same way, because what is happening here is whatever is defined in the formula, it will look first in D. If something isn't in D, then we're calling this LM function from the global environment. So now anything that is missing, it is going to be looking for them outside. So if I say, let's look for Y2, then Y2 is not found. Yes, so it should be the same. And then if you put it into the data frame and change it outside, it is still going to be using it from the data frame. So that's why it's probably a good idea to have it as part of D.
Okay.
So just leave it there. Thank you.
Thank you.
So some of these so-called methods, like summary, coef, and fitted, are quite widespread and used not just for linear models, but for other GLMs, which are generalized linear models or mixed effect models. And these just refer to the coefficients. And then the summary, if I print the summary, that has like the estimate, which is provided by coef. And then you can also get a sense of the residuals. These are super nice. Like median is close to 0, and then the mean and the max are very similar, just the sign is different. That means you have a nice normally distributed residuals, which is quite rare in actual real data sets. But because we simulated this, it looks much nicer. And you get some R-squared values and degrees of freedom and little stars. And anything here is significant. And the way how the significance is assessed, that you have an estimate, and then you have some standard error, which is something we'll circle back to, what the standard error means. But then you compare, if the standard error is huge compared to the estimate, then you can't really say it is different from 0. So if this would be like 25 instead of 0.25, then this wouldn't be significant at all. So if relative to the effect size, your standard error is reasonable, then it becomes significant. So it's really depends on the ratio of the two, and then you compare that to the t distribution and what you would expect based on asymptotic theory. Now, there is another parameter which is not here, but is kind of used to calculate things in the summary, and that is our sigma value. So this sigma is, it relates to the residual error. So what you see here, residuals are ranging between these. So what I can do is I can calculate maybe y minus fitted M3. These are our residuals, right? And I can plot them or get a histogram. So this is the histogram of the residuals, and this is what the summary means here for the residuals. If I just straight up calculate fitted value minus y and take its standard deviation, that is going to be very close to this sigma. So this is what it means, the standard deviation around the residuals. And it's slightly different because how it gets calculated is slightly different than just calculating a standard deviation. It is based on a maximum likelihood estimator, and that's why it's slightly different, but you can see it is very close. So now here comes the fun part. This is something we've seen before. Our observed values and the relationship that we are after, mu versus x. Now we can add the fitted values from model 1, 2, 3, 4, 0, 1, 2, 3, with just the intercept x, x and x squared, and so on. Now you can see the black one is intercept only. So we say, well, we know the mean, so it should be somewhere around the mean. So if our guess is the mean, we can't be very far off. If we know the values of x, now we can fit a linear model that is truly linear. So we get a line, that is the red one. Then the second order polynomial is going to be this green, and the third order polynomial is the blue. Now this blue is getting very close, right? So if we keep adding maybe x4, x5, x6, as we have in D, it is already there. So you might say, we're going to use it at some point, and that's true. So if we keep adding those and fit the linear model, then we are going to get better and better fit along this line. And if we still deviate, that's because we might need more sample. So if you increase sample size and increase model complexity, you're going to get close to the truth. But you can also go beyond truth in the sense that when this line becomes too flexible, maybe you are connecting all the points and it becomes this zigzag, that is an overfit, right? We don't really want a zigzag. So we want something in between that is a reasonable approximation, but is not overfitting. So to be able to do that, we will have to calculate some kind of error metric. And before we do that, let's check how we can quantify uncertainty around these estimates. And here's a function that I'm not going to explain, but what it does is we made this calculation to get the fitted value. Now, we know that there is this residual error around each of the points. So what this is trying to do is we look at some parts of the summary that we haven't talked about yet. Let's say the standard error and where this is coming from. There's a function called vcov. And if I use the intercept only, I get this 1-by-1 matrix, which is our variance covariance matrix. There is no covariance involved here because this is just the residual variance. So if I just pull out some parts of the summary, which is the first two columns, now this is the estimate we saw where that's coming from, and the standard error, that is the square root of the variance. So it is a standard error, and when you look at the residual has variance, and the standard deviation is the square root of the variance. So in this sense, that is our asymptotic standard error that we get in the summary. And this variance covariance matrix is the other very important thing that comes out of every optimization or maximum likelihood approach, although LM is not using maximum likelihood in the sense of optimizing any function because there is an analytic solution to that. But when you have to optimize for convergence, then you would use the coefficients, coef, let's say M3, and then the variance covariance matrix is a byproduct of that. So if you evaluate the likelihood function at these values, at the coefficient values, you're going to get, so if you imagine a multidimensional space and each dimension corresponds to one parameter, the function that you're maximizing has a peak in this multidimensional space. And whether it's very sharp or very not sharp, like a flat, that is going to be your estimate of a variance. So if you are really certain about that estimate, then the uncertainty around that is going to get smaller, which gives this function a big peak. So this is really trying to capture that hard to visualize multidimensional space and tell something about how these parameters are correlated with each other, which is something you can grab from the covariances. And also in the diagonal, you get the variances. Maybe this is a bit more statistical than required, but let's just focus on the diagonal. So this is the variance covariance matrix for model 3. This is the estimate and the standard error. And if we pull out the diagonal from the previous matrix and take the square root of it, that is going to be what is displayed in the summary. You see, this part of the summary is identical to this one. So this is how the summary is put together. And now why I'm talking about the uncertainty is that there are two kinds of uncertainties. One kind of uncertainty is this, the standard error around our estimates. And if you have 100 observations and you go out and double the sample size, then this is going to get smaller. What isn't going to get smaller is that sigma, what is the residual error. So no matter how many more data points you collect, there is going to be some other aspects of the model that you can't really reduce without extra information. Maybe extra information is that you can use more polynomials, or maybe you have Z, something like that. And that other concept I wanted to bring up is called prediction interval as compared to confidence interval. Can I ask you if anybody knows the difference between the two?
I had not heard of them before.
Okay.
I'm wondering how we are to interpret that the standard error is getting larger from up to X to X.
Yes. You mean that it's 0.18, 25, 36?
Yes.
I wouldn't attach too much meaning to that. It's just what it is. So if you have like a bell-shaped distribution and you have a mean, think about that as your coefficient, and how wide or narrow that distribution around that mean is, that is going to be your standard error, right? So am I really certain that X, like the beta corresponding to X, is 1.8? Like compared to 1.8, 0.25 is like one like seventh of it, which is pretty small. So now if you have to assess, here is 1.8, here is 0, does that distribution overlap 0 or not? Or is it like really well defined and 0 is far off? It is very unlikely that this coefficient is 0. That's what the standard error is telling you.
Yeah.
So it is really relative to the effect size. And that's why people often scale the variables. Like you can scale X to have 0 mean and unit variance. And if you do that with X, Y, Z, and every, well, not the response, but all the predictors, then you can compare the effect sizes in the sense that 1.8 compared to 0.5 is going to say that variable has a lot more effect. But in this particular case, the units are similar except for the power transformation. But when you have variables on different scales, if you measure something in kilometers and get an estimate, now if you put the same data but in meters, you're going to get a different estimate because their product needs to be the same. So if 1 times the coefficient or 1,000 times the coefficient, you're going to see the corresponding reduction on the other side.
Right.
So it really comes down to what the units are, and relative to that unit, how far you are from 0. And one thing that is totally meaningless in my mind, summary M3, is this standard error for the intercept. I mean, that is meaningful, how well we can estimate that, but these stars, are we really interested in the intercept being 0 or not? We're not really testing that.
Right.
For other things, yes, we could, but for the intercept, it never happens. That is just, if X is big, then the intercept is going to be big. If X is small, that is going to be small. All right. So now this is going to be interesting. We pick one model, not, and let's just stick to asymptotic, which is what you get here, the standard errors and the variance covariance matrices. So this asymptotics means in statistical theory that eventually, if you have infinite sample size, things are going to converge to a certain distribution, which is going to be multivariate normal with mean of this. And our estimate of the variance covariance matrix is this. So with these two pieces, you can define a multivariate normal distribution. And from this multivariate normal distribution, you can generate other potential coefficients, which is if you collect a different set of data, the coefficient should come from this distribution. That's what it is saying. If you collect more and more and more and more data, then eventually things are going to converge to this theoretical and nice distribution. So that's what asymptotic means. So we are using the variance covariance matrix and the coefficient vector. Now, maybe I'll show you first and then explain the CI and PI. And probably I need to source this function as well. This is the graph that is not telling too much, right? So this is our intercept-only model. We know this is the gray line is the truth. We have some error around those. That is what we observe. And we're trying to approximate this curve. But now we are just saying we have the mean. Now the confidence interval is this purplish area around the mean. So that is like the standard error of the mean. It relates to the sample size. If we have 1,000 samples, this becomes narrower and narrower. That is our confidence interval, how confident we are in our estimates. The prediction interval combines this one, the confidence interval, and the residual error. And what it needs to satisfy is that we might say we want this prediction interval to capture 95% of the observed data points, which is kind of true. There is 1, 2, 3, 4, or maybe 3 or 4. So I can calculate how many of y's fall between the lower and upper values, and this is what this function spits out, CI versus PI. The fit is the same, that is this line, what our expected value is. Lower and upper, you see this is much closer to the fitted value, that is our confidence interval. And the prediction interval is on top of that. They're also going to use what the residuals imply. So we would say this is the range along X where 95% of our data points are going to be located. So if we need to make a prediction, it's 3%. So exactly the same, three dots were outside. So if you want to make a prediction for an unobserved value of X, let's say 2.1, then we would say, well, it's somewhere between -5 and +2. That is not very informative, because no matter what the value of x is, our prediction and prediction interval is going to be unrelated. Now let's see what happens if we use M1. This is a bit better, but still miss like 4 data points, 1, 2, 3, 4, around 5, right? So that's our target. And now we see the confidence interval and the prediction interval around this fitted line. And why we see that it widens at the edges is because now the uncertainty is for the intercept. When the intercept is higher, the slope gets lower. When the intercept is lower, the slope gets higher. And that's why you see this hourglass-shaped interval around the line. But the prediction interval is pretty much unimpacted, although it is getting narrower. So if we calculate the difference between these high and low points compared to the previous graph, it is getting shorter and shorter. Let's try M3. Now we get the line very well, and also our prediction interval is going to be wide, because the point of that is that this is the range where any new observation will be with a 25% certainty. So if we make predictions 100 times, we're going to be correct within this range 95% of the time. So that is the difference between our confidence interval and the prediction interval. Any questions so far?
That's helpful to go back over the theory. I appreciate it. I'm relearning things. Thank you.
Yeah, so it is not always just the fit, but it is also the uncertainty around that fit and what that implies when you make predictions. And this is all related to a simple LM function. And it only gets more complicated from this. So we have the fit, which is this line, how close we are to truth, but unfortunately, we don't know truth, right? So if we look at this and we see, well, black is close to the gray, so we are good. But the problem is that we don't know the gray line exists or what that shape is, although we kind of look at these dots and we can guess what that might look like, but we cannot really compare to that. So how can we make sure that we are not doing something like this? Plot y along x and type equals L. So this could be our extreme overfit, right? If we were to estimate as many parameters as observations, this is what we would get. So somewhere in between having just the mean and having no degrees of freedom left, but just each data point becomes its own parameter and we get this zigzag. What is that optimal complexity that we want to shoot for? And this is where this bias-variance trade-off comes in. So if I go back and plot this thing again, so if I look at my fit, which is the black line, and how far the dots, my observations are from this line, this is going to give me my residuals, y minus expected value of y. And if I calculate this and take the mean, that is going to be the bias. If it's close to 0, that means my estimator is unbiased. If it goes into the positive or negative, that means you're over predicting or under predicting. So your estimator is going to be biased. So this bias and its squared term plus the variance is going to be your mean squared error. And this bias variance trade-off states that as you increase the complexity of your model, and here I'm just going to run many simulations one after the other. That's why we will repeat the simulation. You see, my new y becomes mu plus some new error. So mu stays the same. This relationship will never change. But now I'm adding different error to it, which is like drawing new data points from this relationship. So this is what this function is going to do. It returns a vector of new observations. Now I will take that and the existing D data frame. So maybe that's why I left it out at the first place. So D shouldn't have Y because we are going to create new Ys. And I'll fit the first degree, second degree, third degree, up to sixth degree polynomials. And then we'll make some predictions for those. And then we compare the predicted value and the known truth, which is our mu. So we can calculate bias and variance because theoretically you need to know truth to be able to construct this diagram. And that's why it is really hard for real data. So what we are going to play with here is just to see if this is really true. And I just looked it up on Wikipedia. Bias, variance, trade-off. And if you look for images, this is what you find. Oops. Something like this. As the model complexity increases, variance is going to go up, bias is going to go down. And you want to find that optimum when the total error is minimal. And the goal of this next exercise is to recreate this diagram using LM in R. So this is just for one iteration because we are going to run multiple hundreds. So we can get new observations. And if I plot this, it's going to be very similar, y obs versus x, but not the same as our y before that we originally did with the seed set. Kind of similar, but it's not the same. It's like repeating the experiment once again. This predict function will just fit all these models in one go, and variance bias function is going to calculate the bias and the variance. So this is my prediction, my point prediction based on the different models, and then this is my bias and variance. The next thing is going to just run it 200 times, and hopefully this plot will look okay. So this is what we get. Not quite this, but something similar. The variance goes up, the bias squared goes down, and the sum of the two, which should be proportional to our mean squared errors, there's an unreducible variance component added to this, but where it's minimum is probably model complexity 4. So there is really an optimum value, which is slightly above to third degree that we've played with so far, but less than 6. Okay, that was variance bias trade-off. Any questions so far? We have something in the chat. Let us step away. All right. Anyone else? Questions so far? So this was the stats heavy part of today's tutorial. And I'm going to be using a couple of other approaches now. So not just LM, but maybe a generalized additive model or a boosted regression tree, so that we can see how we can estimate this relationship in using different packages or functions. Are we good to go on? I assume so.
Well, before you go on, could you draw the bias variance graph again?
Sure. I don't know why I cannot go back to it. And I scaled by the max, so this is not the true squared error scale, but just something I scaled so that it looks nice on a graph. So this is model complexity, x plus x squared, and this 6 is 1, 2, 3, 4, 5, 6 degree polynomials. And the variance becomes bigger because you are estimating more parameters. And because they are correlated, you never know if one goes down slightly, how that is going to impact the others. And that's why overall, the variance is going to increase because you have to estimate more things from the same amount of data. So if sample size is fixed, if you keep increasing model complexity, your variance needs to increase. You can decrease variance by collecting more data. And bias is like how well you fit the observed data. So if you connect all the dots, that is your perfect fit. Compared to that, a straight line is going to be as far off as possible that we've seen like along the mean. And somewhere in between, you go from here down to here.
Okay, so this is telling us the optimal model complexity was 3.
Yes. Or rather 4, I think, because you're not looking at where these two lines cross, but you're looking at where the sum of the two lines is minimal.
Oh, okay.
So this MSE, mean squared error, is variance plus bias squared, plus a constant value, but that is not going to impact the minimum. And that is right here.
Okay, thank you.
You're welcome. So we set the seed to 3 and make a new data set. Plot y against x, lines mu versus x. So this is our new data set. This is how it looks. So first, we repeat what we did before with 6 models of different complexity, and we can calculate something called AIC, which is the archaic information criteria. And you can see it prints out the degrees of freedom, how many parameters you had in the model. So this is 3 because M1, it has 2 coefficients plus that residual standard error, which is our sigma parameter. 2 plus 1 is 3. That's why df is 3 here. And as you increase model complexity, you go up to 8, because 6 of the polynomials plus the intercept plus the sigma. And this AIC is going to be minus 2 times the log likelihood plus a penalty that is 2 times the degrees of freedom. So more complex models are going to get a higher AIC, and we're looking for the minimum, which is something we can grab by this which min function, and it says 4. So the fourth value, 1, 2, 3, 4, that is model 4. So AIC is telling us the same as our bias variance diagram using mean squared errors was telling us. So model 4 is probably the best that we can use. What I do here is I put all these models in a list and I pick the best one, which is the 4th. And I just assign that to this object. Summary best is x1, 2, 3, 4. So this is what captures the relationship best given the data that we had. So now going ahead, we have a GAM function from the MGCV package, and GAM stands for Generalized Additive Models. So instead of using many polynomials, so here x plus x squared, x cubed, x to the 4th, and so on, we can just say use the spline of x, which is going to be a flexible function that is a summation of many different functions, and GAM is going to take care of figuring out what is the optimal choice there. So we don't really have to do too much other than say we want GAM y as the function of a smooth function of x, and using the Gaussian family. So this summary is not going to give us exact coefficients, although those are there and you can extract if you really want to do that. It is just going to say, well, this smooth function of x is significant so that it relates to our y. It is not just some noise variable there. But best if we just plot the GAM and see for ourselves. So this is the true relationship in black, and our spline is going to be this curve here, which kind of goes along the black line. But because we don't know truth, it is going to be influenced by our observations. So if you have more data points, this will look nicer. Or if we have a different set of 100 observations, these peaks and valleys might be slightly different, but overall, the pattern is going to get captured. So this is what GAM does. And like we don't really have to do fit 6 models and then pick the best. This is going to do everything for us. So this is really handy, especially if you have not too many variables. And LM was parametric, so you estimated coefficients. GAM is often referred to as semi-parametric because we have some parameters. For example, here we have the intercept plus the spline function, which is the non-parametric part. You can also include maybe z plus the spline of x if you have something else, and then you would get a fixed coefficient for z and the spline for x. So you can combine parametric and non-parametric ideas in GAM. And the next model is going to be non-parametric. This is regression tree. The most basic implementation is R. In R is called R part. And I think this is archaic. Not many people are using it other than for teaching purposes, which is what I'm doing here. So you can load R part, which is part of the base R installation. fit our part with this formula interface, same as before, y as the function of x, and we use the ANOVA method, which is like the Gaussian family. So this dictates how the loss function is calculated, which is really the residuals and how that is being minimized. So what our part is doing, you can see splits here. So the root, this is where you get a mean. And then you look at x and split it somewhere. Where do you need to split x so that the difference between the means of the two groups becomes as big as possible, whereas the within group variance becomes as minimal as possible? That's what ANOVA is doing, which is really within and between group variances compared. So that's how you determine the split along x. Probably you need to go like 0.5, 0.6, split it here, and then left and right becomes the two branches of the tree. And now you repeat the process on the left, then on the right, and you create these smaller and smaller buckets, and within each bucket, you're going to get a mean. Let's see how that looks. This is our tree with the decision rules. As I said, close to 0.6. When it's less than 0.6, you go this side and split it again and again. And this is going to be the mean within those buckets, which has 16, 10, 31 data points. And you repeat the same thing on the right-hand side, which is greater than 0.6. You split it again, you split it again, and so on. Now we can get the predictions and put it back onto our diagram and see. This is what our part is doing. So you split it here, you split it again, and you split it again. This is going to give us this zigzag line, because within each bucket, and by bucket I mean combinations of predictors, here we only have x, so that is going to be an interval of this whole range of x. Within that bucket, you just calculate the mean. In this bucket, this is the mean, and so on. And then we just join those lines. Any questions regarding our part? So what dictates how many splits we make? But there are some so-called tuning parameters, and this is where we are getting into machine learning territory. So these are hyperparameters, not parameters in the likelihood sense that we are trying to optimize for those parameters, but parameters in the sense that we can define how many observations we need in one bucket. So we can say we shouldn't allow less than 20. And then some of these buckets that we saw before are going to get lumped. So if you have like 16 and 10, these are going to be just one node. This is fine. This is less than 20. So this might all get combined together. So these are called hyperparameters, and then you can tune these to change it to 10, to 20, something like that, and then assess the fit and figure out what is the best combination of these hyperparameters.
So,
Now,
hi, sorry, if I could just
yes?
ask one question. So the number of nodes in this. So the optimum. How do we like know the optimum solution? I think you mentioned this just now, but like in this case, because they are just clubbed into one thing here, N16 and the N10 is like clubbed into one thing. So is this the optimum number to use, or is there any other way to find the optimum number of decision trees?
Yes. So what you would do to find the optimum is you would have to set some rules of how to do the splitting or how deep you need to go.
Okay.
So if you set, I think it's called min bucket or something like that in our part. It's part of params, I think. So you can supply, control, output control. Okay. So min bucket,
Okay.
which is calculated by minimum split. And then,
Right.
yeah, so these are the hyperparameters that you can change in the algorithm. And depending on that, you get different numbers, of different splits along X. And now once you have these different splits, you go back and calculate the fitted values and compare them against the observed. And if you do cross-validation, which means you have like 80% to test, train on, and then 20% to test on, then you can do this like 5 times, for example, and then come up with a test mean squared error. And then as you change the tuning parameters, you get slightly different mean squared errors. And based on that, you can find what is the optimal setup.
Okay, makes sense. Yeah, thank you.
And compared to our part, which is a very basic implementation, this Partikit, which I like much better, is doing some of this evaluation. So it takes a statistical and not so hyperparameter tuning approach. So it is looking at significance values from like many different iterations, and it is pruning the tree back. So if you look at this fit plot, first this is the tree. So now it only gives me one split, left and right, and it says that's the optimal thing I could find, and it also gives this distribution summary for the different nodes. And if you then plot this, if I don't see the red line, this is actually quite okay. So now I don't want the red line, or sorry, the black line there. So if this is all I know, maybe this is perfect, right? So if I don't know what the true relationship is, I just see there is left and right, and one is higher than the other. Maybe this is really the optimal solution here. Now there is something called boosted regression trees, or generalized boosted machines, which is what GBM stands for. And what this does, instead of plain regression trees, which is this chopping approach and then taking the mean and then maybe repeating that many times, and random forest is a kind of tree approach, but it is useful when you have more than one variables, because what that does is it picks different x's, x1, x2, x3, and so on. Right here, we only have one x, so there is no point in doing random forest, but we can do boosted trees, which means you make a couple of splits and then calculate the residuals. Now you look at the residuals, which kind of brings everything back together, and try to fit a tree on the residuals. And you keep doing this many times. So this is what boosting does, is that you have, maybe this is where you start, you have a split, you have left and right. Now you calculate the residuals. What is the distance between my line and the dots? And I fit a tree to the residuals. Then I calculate the residuals again, fit another tree. So at the end, when you make a prediction and you have 10,000 trees, you need to make really 10,000 predictions and kind of combine them together. How do we fit GBM? Y follows X, distribution Gaussian, and I have set some of the hyperparameters that you can also tune here using mean squared error. So it said X is important because it had non-zero influence. So if I plot that partial dependence plot, then this is what I'm going to get. This is how y relates to x. And what I did here when I predicted, or maybe I haven't quite done that. So my prediction 3, I take the fitted boosted model. New data is D as before, because I want the predictions for values of x. And then entries, I had 50,000 trees. So each sequentially fit 50,000 trees. Now I want to use the first 5,000, the first 10,000, and all the trees that I have, and predict on the response scale, which for Gaussian won't really make a difference because we have the identity link here. So response and link function scales are going to be the same. So what we do here is plot our original relationship plus the predictions. And this math lines just takes all 3 columns, because head PR3, we have the prediction from 5,000 trees, 10,000, and 50,000 trees. You can see here that the 5,000 is very close to our previous this is not a very good fit. I wouldn't be using it. But the red is kind of getting there. And maybe there is some scaling issue here. But using 50,000 trees, which sounds like a lot, you can see it's really fine scaled jagged line, but that is not really joining all the dots, but it is still like a reasonable fit, goes along our unknown black line. So this is how we would use boosted tree to get our predictions. And there's another very interesting method, which is more similar to LM, but there's a penalty included. So with LM, we fit 6 different models and we picked one. Instead of that, you can just do estimation and model selection in one go. And that is called penalized likelihood, or sometimes you can hear ridge regression or LASSO, or maybe elastic net, and there is something even newer than that. Lots of different versions. What this does is, given your parameter estimates in the sense of LM, intercept, X, X2, and so on, if you use these to get the fitted value and compare that to your observed, plus you add the penalty function, which relates to either the absolute value of the coefficients or the sum of squared of the coefficients. One is the LASSO penalty, the other is the ridge regression. You're going to get slightly different answers, but it all is going to basically make some of the coefficients 0 and some are going to get an effect. It is a bit hard to explain without proper visuals, but let's get some of those going. First, we need to scale D. So we had X between -1 and +2, as I recall. So we scale everything and call it XX. So now, summary XX, we'll see that mean is going to be 0 because we centered it around the mean. And if I calculate the variance, that is going to be standard deviation of 1. So this way, you can shrink the coefficients without having to worry about the original scale of the predictors. And this is a prerequisite for this regularized approach. And there's a package and function called glmnet, which can fit all these different options. Alpha equal to 1, this is the LASSO, what we're going to do. Alpha equals 0, I think that is ridge regression, and somewhere in between is things that combine the two approaches. And the penalty is called L1 norm, which is sum of the absolute value of the coefficient, that is L1 norm. And as you change that penalty, and that combined with a lambda value, which is this scaling parameter or shrinkage parameter that we are looking for, what is the optimal value of that? As that is changing and the L1 norm changes with this lambda, you see coefficient 1 increases and then stays constant. Coefficient 2, after some lambda value, starts increasing, and so on. So this is called the path diagram, and you can see what is the value of each coefficient in the active set, and by active set they mean non-zero coefficients. So it's like, let's just pick one, which is x. Along x you have high and low, so this is almost like fitting a line. Once you have 2, 3, 4, you are going to see the nonlinearity kicking in, and as you increase more and more, you see all 6 coefficients at some non-zero value. Now the question is, which is the value which is optimal? So there's a cross-validation function in GLMNet, which is going to give you what is that lambda shrinkage parameter value is that gives you the best result. And if you pull that out, CV lambda min, that is 0.0065. So the log of that would be -5, which is this line here. So this is where it found the minimum. So if we use that minimum lambda and predict based on that, then now we have our 4th prediction. Let's see how that looks. Pretty cool, hey? So this is another way where you don't really have to worry that much about model complexity, because you can find an optimal complexity based on cross-validation and using this LASSO regression. And finally, I have 2 more things to do. One is a prerequisite for bagging, which is called bootstrap. So bootstrap is a way to characterize uncertainty when it comes to parameter estimation and prediction without having to make too heavy assumptions about the distribution of these parameters. So you only need point estimates. You don't need to know if like the distribution of that parameter is skewed or non-normal or anything. You just need the point estimates. And the idea is that you collected 100 data points. Now, if you imagine you would do the same experiment again and again and again, you would get something similar. And you can achieve the same thing by resampling your one set of data. So if you have 100 observations and you have IDs 1, 2, 3, 4 up to 100, what you need to do is sample with replacement, which is what we do here. So let's say I have 10 IDs. Think about these as rows in the data frame or just IDs for observations. Observation 1, 2, 3, 4, 10. What I can do is I can sample with replacement. So you see, now I get 10 IDs again, but I have some more than ones. So if I sort them, you see 1, I don't have 2 and 3, I have 4, 5, 5 again, 6, 6, 6, 7, 7, 10. So this is what happens with replacement. Some of the observations you are not going to get, some you are going to get more than once, but altogether sample size stays the same. And if you do this enough times, let's see what happens. Now BB, capital B is just how many times I want to repeat the whole thing. And BB becomes this matrix where I have 100 rows and 200 columns. So these are my random IDs. When I'm refitting the model, I would take column 1. This is going to give me the row IDs that I need to take from the data frame. Then the next time I take column 2, column 3, and repeat this up to 200. So I did this before, the same thing, what we did on the polynomials and find the best one, which is, again, 4th order polynomial. Now what I do here is I just say that is the best model. I already know that. So I'm just going to fit the same model to different subsets of the data that I got from resampling. And I set up a matrix filled with zeros, 100 rows, 200 columns. And this is just to store my predictions. And then I write a loop from 1 to B, which is 200. And then I fit the same model, but to this subset of the data, right? I take the ith column from the BB matrix, which is going to tell which rows to pick from DD. And we have DD defined as this data set, like the model frame from the best model, which only has the columns that we need. So I take this subset, fit the same model up to 4th degree polynomial, and then I make a prediction and put it in PR math. Now for each row of PR math, which is like 1 means by row, 2 would mean by column, I apply the quantile function. So 1 row looks like this. This is 200 predictions from the bootstrapped data, and it is going to have a distribution like this. So this is my first observation and my bootstrap-based prediction around a point estimate. And if I do that for each row, I'm going to have what? What kind of intervals am I going to get? Confidence or prediction?
Confidence in?
Yes.
Okay. Confidence.
Because I'm not adding that residual error.
Residual, okay.
And I just take the quantiles.
Okay.
So if I have 200 values, I just chop off the 2 tails, and whatever is inside the 5th, 2.5th and 97.5th, which in between you have 95%, that is going to be the interval that we are after. So what you see here is a usual true relationship along the points, the black line. Then each gray line is one bootstrap iteration. We have 200 of these, and you see that it becomes really thick in here. So the red one is our mean value, and the dotted line is the confidence interval, which is based on the quantiles of the gray lines. And this is how you would do bootstrap for a linear model when you fix the model. So M4, that is our model. And the only thing we change, like right here in this loop, y is a function of xxx. The only thing we are changing is the data, but the model stays the same. Now, compared to this, bagging is when you don't make this assumption. You take the new data and you repeat the whole thing. 1, 2, 3, 4, 5, 6, calculate some AIC or mean squared error, pick whichever is the best or most optimal, and you repeat the whole thing 200 times. So you're really fitting, in this case, 1,200 models, right? Each resampled data gets 6 models, and you repeat the whole thing. So we create another data frame with all the 6 columns that we need. DDD, you see X, X2, and X6, everything is there. And then this is our function, which takes a vector of our resampled IDs, like which column to pick from this BB matrix that we already created, and fit 6 models, calculate AIC, pick the best, and make a prediction based on the best model. So this is the frequency of the best models. The M4 was most often picked. So out of 200, there's this. So MID is I'm pulling out this attribute that I saved, which model was the best. So I can summarize that, and number 4 got picked 84 times. Next was number 6, which is this. That was picked 75 times out of 200. So it's kind of very similar. So either complexity 4 or complexity 6 is going to be most optimal depending on what data set you have. And putting it all together, this is your prediction, which looks very similar to the previous bootstrap, actually. But this is based on fitting a different model each time, if that's what the data dictates. So these were all the different spins on the very basic LM function from R, and they were trying to approximate this nonlinear relationship. And happy to take any questions if you're still not asleep after me talking this much about LM.
One thing about the bagging thing is like the bagging is like it just take one sample of the training data, and then that's one bag, and the second bag is take the different set of training data, and then that second bag, and then do the different model, right? So in this case, the cross validation is not so bagging is like, is it not required?
In a sense, yes, I was not doing cross validation. In this sense, I was doing bagging in the sense of picking a different set of predictors, like either just 1, 2, or 3, or all 6. So bagging could be what predictors you pick, and then based on some criteria you evaluate which is the best set to pick.
Okay. So
and you combine this with resampling or cross validation.
Okay. So what I thought was like you pick the predictors, not the data, the vertical data. Like so if you have like 100 observations, 80 observations is going to be in the training set, and 20 is going to be in the testing set. So backing, it means like you have 5 predictors. It's gonna take 3 first. It's gonna take 4 first. That is backing. So okay, now it makes sense. I thought like in the 80 observation, it's going to take 20 first, it's going to take 60 seconds. I thought that is bagging. So, okay, it makes sense.
Yeah, so how you pick the rows is
Okay.
the bootstrap part, which is in this case resampling. So it's not really cross-validation, that 80-20, but it is just kind of combining the bootstrap with this bagging approach is like the most complex, but in the way you don't force that this is the model I picked based on one data set, and now I'm just going to assume that's the true model, right?
Okay.
But you pick a data set and let the data tell you which is the best model to use. And then this way you have to keep track of the rows and which columns were used.
Okay, makes sense.
Anyone else have any questions? If not, I hope the dinner is ready. And I know some of you were cooking while we were having this conversation about LM. And so next month, the Edmonton R user group is going to have a hybrid event, a 4-hour-long session about hierarchical models, which is something that we haven't talked today. And if you're interested in that, you can find the info on the Meetup site, and there is a link where you can register so that it can send you instructions about how to set it up. If you are in Edmonton, you're welcome to join us. I'll let you know where we are going to meet. If you are calling in from various other places of the world, you're welcome to join online.
One other thing, will this file be shared with the group members or something, or no?
Yes. So there is a website where you can go. And I'm going to post this file, a compiled PDF and our Markdown version, plus the video, if I like the video. Well, if there are no more questions, thank you very much for joining me today. Hope it was somewhat informative to talk this much about the most basic stats function in R. And well, let me know if you have any questions or follow up with me, and I'll send out links in a couple of days.
Yeah, thank you, Peter. It was very interesting. I'd never really seen the results of a decision tree plotted as a regression like that. It was kind of interesting to see how stair-stepped it looked.
All right. Thanks so much.
Thank you, Peter. Good night.
Enjoy the rest of your evening, and see you next time.
Yeah, good night. It's like 10 p.m. for me. It's like, yeah, good night. Bye.
Yes, it's getting late.
Yeah.
Take care.
Take care.